Okie dokie, Unit 6, Lesson 12. We want to be able to find integrals using trig substitutions. And we're looking at a bunch of tables for some bizarre reason. So let's see what the truth is. Okay, so we want to find integrals using trig substitutions. Recognize this example that we worked through the other day? All right, there it is, step by step, all the way through. And so let's just move the answer up next to the question. Because we also, our very first example was this one we did. And there's the answer we got. Right, now we can do this again and again and again, and we're going to notice something. There are a lot of things that are identical. Right, look at all the different pieces of those solutions that are identical. And then the things are a little bit different. Aha, look at how that 9 repeats itself. And of course, the square root of 9 is 3. And look where that's located. On the other example, look at that 25 and how that 25 repeats. And of course, the square root of 25 is 5. So some of us are thinking, hey, I should just memorize the different pieces. Some of us are thinking, I don't know if I'm going to be able to memorize that, but boy, it sure would be nice to have a reference sheet I could look at. So if we had to evaluate this integral, we know most of the pieces already. We just got to plug in 1, 2, 3 things. You say, hey, I know where that 49 is going to go. I'm going to have 49 over 2. I also know that 49 is going to repeat inside that square root symbol. I also know the square root of 49 is 7. There's the solution. Right? Saves a lot of work. Now, remember the day when we found the area of a circle and we worked through this as an example? And when we were all done, we had 100 pi square units. But of course, to do that, we rewrote it in terms of theta, and we changed the limits of integration. So instead of negative 10 to positive 10, we had to do negative pi over 2 to pi over 2. What if I didn't want to change to d theta? What if I didn't want to rewrite that integral? Well, we know that coefficient of 2, being a coefficient, it's just going to sit there. We can actually put that out in front of the integral symbol. All right, when we take derivatives, the coefficient just sits there. When we integrate, the coefficient just sits there. And now you're like, oh, I know how this is going to play out. Right, 10 squared is 100, so just make sure I put 100 in all the proper places. Square root of 100 is 10. I got to make sure I put the 10 in the correct spot. And I just evaluate this expression at positive 10 and negative 10. So everywhere I see an x, I can plug in positive 10. Everywhere I see an x, I can plug in negative 10. Go through and do some simplification. And then, surprise, 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 look at all of the zeros we have. Right? 5 times 0 was 0. Right? Those two terms cancel out. Of course, half of 50 is where those 25s came from. And of course, 25 plus 25 will be 50. Times 2 will be 100. And of course, we get 100 square units. Of course, we should have known this before we started, right? Because we know the area of a circle is pi r squared. And so if the radius is 10, of course the area is going to be 100 pi. But we could do that with calculus. All right, so anytime we see an equation in that format, we know what's going to happen, right? We're going to have a squared over 2 times arc sine of x over a plus x times the square root of a squared minus x squared all over 2 plus a constant. So let's hang on to that, right? So if that's our integral, and we know that's how it works out numerically, we can say, hey, in general, a squared minus x squared, that's what it's going to be. Now again, that is one of the 3 types of integrals where we attempted to use trig substitution. We also tried it where the x squared came first inside the square root symbol, right? X squared minus 9. And then we also tried it with the plus symbol in between. Right? There's 2 different ways of writing it with subtraction because it makes a difference which one comes first. But for the addition, there's only one way, right? Because x squared plus 9 is the exact same thing as 9 plus x squared. Well, right, so the x squared could have been second position, the x squared could have been first position, or we could just mix it up with an addition symbol. Those are the 3 things that could happen. So our generic for x squared minus a number is going to be x squared minus a squared. Notice instead of arc sine, we end up using natural log. And then for the last one, where we've got addition in the middle, our generic format is x squared plus a squared inside the square root. And again, notice that we are using natural log. Now, there might be a couple things you notice. Those last 2 look very, very similar. You have to be very careful to notice where some positives and negatives are switched. And then you might notice that inside the natural log, there's an absolute value symbol. That's because we can only take the natural log of a positive number, right? We cannot take the natural log of 0, it's undefined. And we cannot take the natural log of a negative number, that is also undefined. That's why we need that absolute value, so we don't become an issue with the domain. Now, back in the old days, everybody had a calculus textbook, right? Good old book with paper pages. Nowadays, of course, almost everything is online, including textbooks. But in the good old days, if you picked up your big, thick, heavy calculus book and you looked at your table of contents, you would notice something. Near the end of the book, there would be a table, or sometimes this table would actually just be placed on the inside flap of the book that says Table of Integrals. There are some common integrals that are so arduous or darn near impossible to do. Instead of trying to integrate by hand, we consult the table. These are 3 of the such integrals that would be on that table. All right, so if I want to try figure out x squared minus 144, I'll say, hey, I got to go to the table, look at the table, and of course, if we had a textbook's table, there'd probably be like 100 of these different integrals, right? So you have to go find the right one. We're just going to play with 3 of them. So say, I think I know what's going on. I think it's that integral, x squared minus a squared inside that square root symbol. So if I want to integrate this, I just got to make sure that I put that 144 in all the correct places. All right, so that x over 2 won't change. I've got that square root. But instead of x squared minus a squared, I need x squared minus 144, right? Because that's my a squared. And then I need my subtract. A squared over 2 will be 144 over 2. Then I need my natural log. Inside the natural log, the x will stay the same. The plus sign will stay the same. The square root will sit there. The x squared will sit there. And then instead of minus a squared, I put the minus 144. Of course, before I do my little celebration, I got to remember that plus c, right? It's an indefinite integral. I've got to have the plus c. And there's a little tiny bit of simplification I can do, right? 144 divided by 2 is 72. But that's the only simplification we can handle. Whew. Maybe there's another example. Ooh. Now this is super cool because not only is another example, notice that it's a definite integral, right? We know the limits of integration. From left to right on the x-axis, we're going from 0 to 4. All right, so again, if I consult a table, it's like, okay, which one am I going to use? And I look at my table and say, it looks like that's the one that matches. This is an x squared plus a squared inside that square root symbol. So when we integrate, x over 2 will sit there. Square root will sit there. X squared will sit there. Plus a squared becomes plus 9. Our plus sign sits there. A squared over 2 becomes 9 over 2. Natural log of, and then inside that absolute value, the x is still there, the plus sign is still there, the square root symbol is still there, the x squared is there. And of course, instead of plus a squared, we put plus 9. Woohoo! And instead of putting plus c, this is a definite integral, so we're going to have to evaluate using 4 and 0. So everywhere I see an x, I've got to plug in the number 4. And then every place I see the x, I got to plug in the number 0. And of course, if I come across an x squared instead of a 4, it's a 16, right? 4 squared is 16. Or it's 0 because 0 squared is 0. Whew, look at all these pieces that we have to work with now. Right? I had to plug in that 4 for every x. And of course, when it was x squared, it became a 16. Then I had to plug in a 0 for every single x. And of course, if it was 0 squared, well, it was still 0. Okay, 4 divided by 2. Today, that is 2. 16 plus 9, that's 25. 16 plus 9, that's 25. 0 divided by 2, 0. 0 plus 9 is 9. 0, we've got to hang on to that. 0 plus 9, that's 9. Of course, square root of 25 is just 5. Square root of 25 is just 5. Square root of 9 is 3. Square root of 9 is 3. 2 times 5 is 10. 4 plus 5 is 9. 0 times 3 is 0. 0 plus 3 is 3. So we got a 0 in there. That's not going to do much for us. So we are going to have a 10 plus 9 halves, natural log of 9. The minus 0, poof, we don't need to worry about that. But we will have a minus 9 halves natural log of 3. Now, absolute value of 9 is plain old 9. We don't need the absolute value symbol anymore. Natural log of absolute value of 3, again, we don't need absolute value of 3. It's just going to be 3. And I also see a common factor of 9 halves. So we're going to keep the 10. We're going to factor out the common factor of 9 halves. And now I've got natural log of 9 minus natural log of 3. Let's condense those logarithms, right? If we condense, we'll have natural log of 9/3, also known as the natural log of 3. So there's our answer. 10 plus 9 halves, natural log of 3. And that's how I would tend to leave the answer. If you're wild and crazy, you could say, hey, 9 halves could be an exponent, right? I could rewrite it that way. But I'm like, nah, I think it looks a little bit silly. I would just leave it as 10 plus 9 halves times natural log of 3. All right, that's what I would do. Now, if you're curious about what on earth is going to happen with natural log of 3, notice it's barely larger than 1. That's because e to the first power is about 2.7, while e to the second power, of course, is about 7.4. So you're like, oh yeah, e to the first power is not that far from 3. E squared, that's quite a bit different than 3. All right, so that's why when you got the natural log of 3, you can almost predict that the answer, if you use a calculator, is going to be just a smidgen larger than 1. Right? So I would be tempted to leave it as an exact answer, but we all know sometimes you're in one of those crazy physics classrooms, and in physics they love to convert the decimals. And if that's the case, then we can convert the decimals and say, hey, our answer is about 14.9438. And of course, in your physics class, we talk about sig figs, right? The significant figures. And we have to figure out exactly where we should be rounding off. Right? So we've got a worksheet today. But instead of consulting some gigantic table in your calculus textbook, we're going to have a worksheet, and it's a relatively short table, right? There's only 3 different integrals that we're going to play with. So let's have at it.